Now, this is a reminiscence session, but I'm going to do something that's a little bit unusual for a reminiscence session. I'm not going to talk about the successes I made back in the 1970s, but a little bit about, some of the things I did, some of the problems I couldn't solve, because I think some of those problems are still related to problems that still exist in deep neural networks. And the bigger the network and the more capable is Rick Brock says, it's capable of memorizing all the training data. But what it's not capable of is common sense. Danger, AI systems lack common sense, and it's partly my fault. So I'm gonna accept the blame, at least for the problems I had in the 1960s, 1970s. But in my later talk, I'm gonna talk about a grand challenge of what we can do in the next 50 years, and maybe get to real common sense. But my first mistake was before I came to Carnegie Mellon. I was then already actually working on what was then a neural network, one layer, step function, 0 when the value is less than 0 for the input, 1 when it's above 0 for the input, and that's what's called I call a linear threshold function. It's what now is, by many people, miscalled a perceptron. The perceptron had such a function, and it was invented by Frank Rosenblatt. The perceptron concept was invented by Frank Rosenblatt. But if you look at the diagrams of a perceptron, he has a set of sensory units, a set of associative units, and a set of response units. In other words, there's a hidden layer. A so-called single layer perceptron shouldn't be called a perceptron because Rosenblatt never called it a perceptron. So I was trying to figure out how can you build multiple layers of these linear threshold units. And so were other people, because we knew this was a limitation in the perceptrons, but I couldn't figure out how to do it. And I was a math major, so I was looking at it as a math problem, so I thought, well, that looks like an integer programming problem. I mean, integers were 0 and 1, but that's still an integer programming problem. But I quickly suspected, I didn't actually prove, but I quickly suspected that's an NP-complete problem. And so I went off to other things. And then got interested in speech recognition because Janet had these nice patterns of speech. And I said, oh, that's a pattern recognition problem. I can see that as a mathematical problem. And then we got invited to come to Carnegie Mellon. But I already had a background. It wasn't my invention. The hidden Markov process was not my invention. In fact, I didn't even know it by that name. Where I was working as an undergraduate in Summers, they had invented what was called a probabilistic function of a Markov process. So but mathematics is the same thing. I just want to give credit to the original name. But what I couldn't figure out, even though I was at Carnegie Mellon and the hearsay system and the black, some people think that I didn't believe in things like the kind of human knowledge. It wasn't that I didn't believe in it. I couldn't figure out how to do it in a Markov process. So that was my failure at the time. But that's going to be a key of what I propose we need to do more of in neural networks. Neural networks are also not really doing human knowledge engineering. In fact, one of the claims for the first end-to-end speech recognition, I think it was the first, Baidu, one of the claims that Baidu made when they did their end-to-end system is no more human knowledge is needed, or something like that, or no more human engineering. But I think that's actually something we need to get away from if we really want to get to common sense. Because like the hidden Markov process and like the neural networks are just mathematical computations. So I'll show some examples of what happens when you don't have common sense. So I knew about these failures at the time, so I worried about them. But anybody of people who's working in deep learning have probably already seen these examples, but the broader audience may be surprised by what I'll show shortly. Did I miss a slide? Okay. Well, we need it because we need sense. It's not just common sense. It's a broader thing of sensibility. Now I'm looking narrowly at sensibility, and you can see violation of sensibility that's inherent in the way we do the computation with neural networks. In fact, I think my slides are out of order, so I'll come back to that one. So a cat knows how to recognize a mouse. Well, so does a neural network can recognize a mouse most of the time. A cat can recognize a wolf. But a neural network, and this is not actually specific neural networks. I may say a little bit more about that if I have an extra minute. A neural network can recognize a mouse, can recognize a wolf, but it can also be fooled. You give it a picture of a wolf, and if you do just the right, almost invisible changes in the image, you can cause the neural network to think that the wolf is a mouse. That would be a terrible mistake for a cat to make, and cats do not make those mistakes.
You can only make it once.
Mouse can recognize cheese. A mouse can recognize a cat. So even the brain of a mouse has common sense in this sense. I mean, they can't compete with human performance in most things, even though neural networks can compete with human performance in most things. But same thing, they can be fooled. And for those who haven't heard this before, it might sound, well, how could that be? How can this very smart neural network that can memorize millions of items of training data, how could it possibly think that a cat looks like a piece of cheese? Well, the trick is basically when you have something with a large number of inputs, and if you change each one by a very small amount epsilon, on a digital image you can make it be less than the quantization in a pixel. So a human looking at a digital image can't possibly see any difference. But if you give the neural network the higher resolution, you can change it by these small epsilons, but they're in a 1,000 by 1,000 color image. There are 3 million of them. 3 million times epsilon's a big number. So it's caused by the fact that the output is a differentiable function of the input, and the derivatives with respect to the input are non-negligible. They're not all zero. So this then gives the mathematics for that, and I won't take time for that, but it'll be on the record. And so the conclusion is that even if what we're training is neural networks, it's this differentiability that's the problem. And it's not unique to neural networks. Any AI system where the output is a differentiable function of the input can have the same problem. So we need to invent things that don't depend solely on gradient descent. And that's now stating that conclusion just on an isolated slide, so you can easily see it. And so one possible thing is to have what Bikshiraj and Rita Singh and I are starting to brainstorm, is taking knowledge engineering, and obviously on these huge systems, there's no way we can actually do detailed knowledge engineering, but if we can get what Tom Mitchell was advocating that I heard from him, we should be doing human AI teams working together, cooperative between humans and AI, so the human is doing some amount and adding some amount of common sense. Now, humans don't always use common sense, but there's some amount of common sense there. And but in order to be able to do that efficiently enough, we also have to have the AI cooperating in the knowledge engineering. Now, I'm not sure we solved that problem, but we're starting to brainstorm it. So the final thing is that what I mentioned earlier, my evening talk will be about posing the grand challenge of looking at some of the things we might be able to do.